So, we would start our analysis of forced convection, and we have seen that when we have forced convection in a tube with a constant heat flux that is supplied through the walls. So, there can be two different types of conditions. One is a constant temperature condition where the tube walls are maintained at a constant temperature, and the second more common is which is a constant heat flux condition, where through an external agency constant heat flux is provided through the tube walls. So, therefore, as the liquid starts to move in the tube, its temperature will keep on changing, it will keep on increasing, and since we have flow and the flow is, we will assume it to be in the laminar region, and the flow is taking place as a result of imposed pressure gradient as well as gravity. So, we can think of a vertical tube in which the liquid is flowing downwards because of imposed pressure gradient, higher pressure at the top as compared to the lowermost point, and the gravity is also acting in this direction. Therefore, the entire flow, even though it is in laminar region, it will be under the effect of surface force, which is pressure, and body force, which is gravity. We know from our study of fluid mechanics that this type of situation gives rise to a parabolic velocity profile, where the velocity starts to vary as a function of radius, as a function of the radial distance from the central line. So, this parabolic velocity profile needs to be known a priori. That means, whatever be the flow condition, we should be able to solve it in order to obtain a profile of the velocity distribution inside the conduit in order to use that velocity profile in our analysis of the energy balance of the system. So, the first job is to decide about the shell across which we are going to find out what is the rate of heat in, rate of heat out, plus if there is any generation of heat inside the shell which is not there in this for this specific problem, and as a result of all these there would be energy stored, change in rate of change of energy stored in the system, that would be the form of the equation. So, in heat in minus heat out plus generation is equal to the rate of storage. When you talk about heat in into that shell, we appreciate that if this is the shell, then there is flow in this direction. So, with flow comes some energy which we call as the convective transport of energy, and since there is a temperature gradient with the actual position during flow, since the tube walls are heated, there would be a temperature gradient in this direction which would also create a flow, this time conductive heat flow in the z direction, where z is the actual direction. I have a tube wall like this, and the temperature would obviously be maximum near the tube, and as I move in this direction, the temperature would progressively decrease. So, there is a gradient in the r direction, gradient in temperature in the r direction as well. So, there would be conductive flow of heat from a value of higher r towards a value of lower r. That means, from the tube wall there would be flow of heat towards the central line. If the system is different, that means a hot fluid is flowing and the tube wall is being cooled, then the direction of this heat would simply be in the opposite direction. We are deciding about the smaller dimension of shell based on which is the direction in which the temperature is changing. So, we realize that the temperature in this case is changing with z as well as with r. So, any shell that we assume must contain two dimensions, two smaller dimensions, delta r and delta z. So, in order to tackle this type of problem in which the temperature can be a function both of r and of z, the shell, the assumed shell across which we are going to make the energy balance will probably look something like this, which we have drawn in the previous class. So we have a fluid which is coming in and some amount of heat, constant heat flux Q1 being added through the side walls. So it's a case, it's a problem of conduction and convection, especially if we consider the z direction, in which since the temperature is changing and we have flow, so we will have both conduction and convection. Whereas since we are assuming that it's a 1D flow, there is no VR component. So if there is no VR component of velocity for the flowing fluid, then there cannot be any convection in the art direction. So the velocity is 0 in the art direction and therefore no convection. However, the temperature is changing in the art direction, so therefore there would be always conduction in the art direction. So conduction plus convection in the z direction and only conduction is going to be there in the art direction. So this is the situation, and therefore the shell that we are assuming is of length delta z, and it's the radius, the change in radius, the annular area is the cylinder, the annular area of the cylinder, the radius difference in radius is delta r. So we are considering a annular cylinder, annular shaped cylinder inside the flowing fluid, and we are going to find out what is the flow of heat into this control volume, into this shell, due to conduction and convection. So we are first going to write the first condition, which is energy in by conduction at any r, and we will assume that the energy flows in this direction from r to r plus delta r. That is the usual convention that we always use. In is always at the lower value, so in is always going to be at r, and the out is going to be at r plus delta r. And this, once we use this specific convention and stick to it, then the profile will automatically adjust itself based on the boundary condition that are provided. So the energy in by conduction at r, if I take this, the flux to be QR, which is evaluated at r, and it has to be multiplied by the area. So it's going to be the inside area of the annulus, and the inside area of the annulus would simply be equals to twice pi r times delta z. So think of it in this way, that when you have the annular area and you are talking about flow of heat in this direction, so the area that it faces will simply be equal to twice pi r times delta z. So where delta z is the length of the shell that is assumed, r is the radius, inner radius. So therefore twice pi r times delta r would give you the area through which the heat, conductive heat in the art direction, is entering the imagined shell. So the in term would be twice pi r times delta r, and the out term would obviously be at r plus delta r, which would be QR evaluated at r plus delta r times twice pi r plus delta r times z. So that's the out term at z. Similarly, in by conduction at z would be equal to, which is q times z evaluated at z multiplied by twice pi r times delta r. So twice pi r times delta r is essentially the top annular area. So the top annular area multiplied by the heat flux, conductive heat flux in the z direction would be can be written as qz at z times twice pi r times delta r, and therefore out by conduction at z plus delta z, that is at this point, would be qz evaluated at z plus delta z times twice pi r times delta r. So these are all four conductive, these are all due to conduction. When we think about convection, I am drawing the figure once again I have flow, therefore convection, and flow which goes out. This is delta Z and this is delta R. So, the heat, that energy which is coming in by convection, that means with the fluid, would be equals twice pi r delta r times Vz. I will mark this as one part of it, times rho Cp times T minus T naught at Z. Let me explain this once again, but I think you all will remember from your study of fluid mechanics that twice pi r times delta r essentially is this area. So, when you multiply the annular area with the velocity which is in meter per second, so essentially these two together would give you in meter cube per second, which is nothing but the volumetric flow rate. So, this entire part is the volumetric flow rate. When you multiply it with rho, which is the density, that is in kg per meter cube, so these together would be the mass flow rate. And the mass flow rate, so it's m dot, this whole thing together up to this point is m dot, which is the mass flow rate, times Cp times delta T. So, this essentially, and this T naught is some reference temperature, because we cannot have energy, we cannot express energy in explicit form, it is always expressed in relative, and therefore, this T0 is some reference temperature. You can define any temperature as the reference temperature as long as you are consistent and you use the same value of temperature everywhere. So, it is m dot Cp delta T evaluated at Z, that is the energy in by convection, and therefore, the energy out by convection, which is at this point would be simply equals the same area twice pi r times delta r, this velocity which is Vz, the temperature difference which is T minus T naught, all these, the entire thing is evaluated at Z plus delta Z, and we all have the rho and Cp. So, twice pi r delta r Vz would be the mass flow rate, would be the volumetric flow rate, multiplied with rho you get the mass flow rate, and then Cp delta T. However, this T minus T naught is evaluated at Z plus delta Z. This Vz is also evaluated, the velocity is also evaluated at this point, but from our study of fluid mechanics we understand that Vz is a function of r only and Vz is not a function of Z. So, if Vz is not a function of Z for fully developed flow, which we have assumed in order to obtain our expression for the velocity profile, therefore, this Vz can be taken out of this sign, and therefore, your T minus T naught, which where the T is changing with Z, as we move in this direction the temperature will change. So, T is a function of Z, but Vz is not a function of Z. So, we can take the Vz out of this, and T naught is just an datum temperature. So, we add all the 4 terms that we have, all the 4 terms, that is 4 terms for conduction in and out and 2 terms for convection in and out. So, when we do that, and express and divide both sides by twice pi r delta r, what we get is r q r evaluated at r plus delta r minus r q r at r divided by del r. This is essentially the net addition of heat by conduction plus this is the net addition of heat by conduction in the z direction, and also we have the convective term Vz. This is T at z plus delta z minus T at z divided by delta z is equal to 0. So, this is the conduction in the earth direction, net addition of heat by conduction for heat flow in the earth direction. This is net, this part is net addition of heat by conduction in the z direction, and this is the amount of convective heat flow into this control volume by convection. So, when in the limit you take the limit you take delta r tends to 0, you convert this difference equation into a differential equation, and the differential equation would be rho Cp del temperature by del z is equal to minus 1 by r del r of r q r minus del q z by del z. So, the right hand side refers to conductive heat flow, the left hand side refers to convective heat flow. And when you put q r using Fourier's law as minus, these are all flux. So, q r is del t del r and q z is equal to minus k del t del z, variation in temperature with r and variation in temperature with z, and we understand that in this system the temperature will be a function of z. As I move in this direction, the temperature will increase, and the temperature will also be a function of r. As I move closer to the wall, since the walls are heated, the temperature will be more. So, T is a function of z and T is a function of both r and z. So, this is something we have to keep in mind, and therefore, I write this equation, put the Fourier's law in here. I am sorry, I missed a Vz in here. This Vz should also come in here. So, when you put the expression of Qr and Qz on the right hand side, and for Vz from our study of fluid mechanics, we know that Vz is equal to Vz max times 1 minus small r by capital R, where capital R is the radius of the tube. We plug this in from the Navier-Stokes equation, solution of Navier-Stokes equation. Then what you would obtain as the final form of the solution as rho Cp V max, which will obviously be at the central line, 1 minus small r by capital R whole square times del t del z is equal to k times 1 by r del r of r del t del r plus del 2 t by del z square. So, this therefore now becomes my governing equation. And this governing equation will have to be solved with appropriate boundary conditions, which we will discuss later on. The point that I would like to make here is that in order to obtain this governing equation, we have to go through a complicated process of finding out what is going to be my smaller dimension for the assumed shell. And since the temperature is a function both of r and z, therefore, for this kind of two dimensional temperature variation, the formulation of the entire problem becomes one order of magnitude more difficult than the case where the temperature is a function only of one direction. So, for a very simple geometry of flow through a tube, when the tube walls are heated, we see that we are having problems in visualizing the shell, and we have to ensure that we are putting the values correctly, the expressions correctly, and finally we arrive at a solution, arrive at a complicated governing equation starting with the fundamentals. We cannot expect to do this every time we come across a problem. So, anytime we see a 2-dimensional or even a 3-dimensional problem, if we have to go through this process, then that's repetitive, that's unnecessary, and there must be a more general method to solve for situations like this, which would necessitate the formulation, the development of a generalized equation which can be used for any geometry, steady or unsteady, and so on. So, this is the background. This underscores the requirement of a generalized treatment, which I am going to start now. And I will come back to this problem. I will come back to this problem and show you that from the generalized equation of energy conservation in a system where flow in and out, where it's an open system where we allow the fluid to come in and leave. So, if we have that kind of a general equation, it can very quickly be resolved to obtain the governing equation like this, which we have obtained after a long series of analysis, thinking, and so on. So, we start our next assignment, but I will come back to this equation, next assignment, where we are going to derive, at least conceptually, the equation of change for a non-isothermal system. So, this is the keyword, it is a non-isothermal system, and we, as before, we assume a stationary volume of as I said before. So, this is stationary with respect to x, y, and z, and fluid is allowed to come in and go out. So, fluid in at x, y, and z faces through x, y, and z faces, and the fluid out through faces at x plus delta x, y plus delta y, and z plus delta z. So, this is how the fluids can come in and go out of this control volume. So, if I write the equation, energy equation, the conservation of energy, if I write the conservation of energy for such a system, then one can write as rate of accumulation of internal and kinetic energy So, this is the rate of accumulation of energy, and look that I not only have taken into account internal energy, I am also going to consider the kinetic energy of the system. So, this is the total energy of the system, and this is going to be equal to the algebraic sum of rate of internal energy and kinetic energy in by convection minus the rate of internal energy and kinetic energy out by convection. So, since we have a flow, then with the flow some amount of internal energy, and because of the flow some amount of kinetic energy is entering the control volume and also going out of the control volume. So, this is the net addition of internal and kinetic energy to the control volume because of convection. Then I can do the same thing here for the conduction, and in the case of conduction I am not breaking it into two parts. I am simply using the word net, which essentially tells me it is the difference between in and out. So, the net rate of heat addition by conduction. So, this is by conduction. However, there is an extra term which we are putting in here is the net rate of work done by the system on the surrounding. So, let us see once slowly what we have done. I am writing the energy conservation equation, which simply says that the rate of energy in, and by in I understand that it is going to be convection and it is going to be conduction, minus rate of energy out by convection and by conduction. So, these terms together it is essentially the net rate of internal and kinetic energy which is added to the control volume, and the mechanisms by which this net addition is going to take place is a combination of both convection and conduction. So, depending on the situation at hand, I can have both present or I can have just one present in the system. So, I can never stop conduction if there is a temperature difference. So, therefore, it is going to be either conduction plus convection or only conduction if we are talking about a solid system. So, if the system does work, I am talking about the internal and the kinetic energy. So, if the system does work or the work is done on the system by some agent in the surrounding, then its internal energy or the total energy of the system will change. So, if the system does work, then its energy gets reduced. If work is done on the system, its energy will increase. So, when we talk about the rate of accumulation of energy, both internal energy and kinetic energy, the rate of accumulation of energy inside the control volume, it must be equal to the net rate of heat addition, energy, I should not say heat, the net rate of energy addition by means of conduction and convection, and an additional term which will tell us, which will give us the rate of work done by the system or on the system. If it is by the system, it will be negative. If it is on the system, it is going to be positive. So, this equation, what you see over here is nothing but the first law of thermodynamics for an open system. And when we talk about open system, that means we are allowing fluid to come in and go out of this. So, from this generalized energy equation, we can we can subtract the mechanical energy equation and we can obtain the more commonly used thermal energy equation. So, the equation that I have presented, that I have shown you, is for the total energy, which contains both the thermal energy part as well as the mechanical energy part. So, from this equation I am going to subtract the equation for mechanical energy, and what I would obtain out of is the more commonly used equation of thermal energy. So, the thermal energy balance equation, considering both conduction, convection as well as the work done, which is nothing but the first law of thermodynamics for an open system, is the generalized treatment of energy transfer in a system, which should give rise to the equation that we are looking after, a general equation for energy transfer. So, this is the one which I am going to continue in the next class, and will revert to the problem of forced convection in a tube with constant heat flux, and we will see how quickly one would be able to obtain the governing equation by choosing the right component of energy equation and cancelling the terms which are not relevant for the problem at hand, the same way we have done for the Navier-Stokes equation.